Hello, my dear students. Welcome back to IKSR chemistry classes. Here we are in lecture number 6 on the chapter Solid State for chemistry students of class 12. This video will also be useful to JEE and NEET aspirants. In this video, we will discuss the efficiency of packing or packing fraction in various types of unit cells. But first of all, let us recapitulate the findings of the last video. These are some types of unit cells and the number of particles per unit cell are given here. In simple cubic unit cell, there is only one particle. The number of particles in body-centered cubic unit cell is 2. In face-centered cubic unit cell, there are 4 particles, while the number of hexagonal close-packed unit cell is 6. Let us discuss efficiency of packing, which is abbreviated as EOP. The percentage of the space of a crystal or unit cell which is utilized in the accommodation of particles is called efficiency of packing. Mathematically, it can be expressed as follows: efficiency of packing is equal to volume of particles per unit cell divided by volume of unit cell and multiplied by 100. Now, the similar term packing fraction, which is abbreviated as PF. The fraction, not the percentage, the fraction of the space of a crystal or unit cell which is utilized in the accommodation of particles is called efficiency of packing. And mathematically, it can be expressed as follows: packing fraction is equal to volume of particles per unit cell divided by volume of unit cell, and it is not multiplied by 100. It is multiplied by 100 in efficiency of packing, but in the case of packing fraction, it is only a fraction, not percentage. Let us consider simple cubic unit cell. Let the radius of particle or a sphere in simple cubic unit cell be r. This is the diagram for simple cubic unit cell in which 8 particles are present at the vertices of the simple cubic unit cell. This is the edge length of simple cubic unit cell and it may be represented by L. In actual practice, all these 8 spheres touch each other and L is equal to twice of the radius of a sphere. L is equal to 2r as evident from this diagram. The volume of particles per unit cell in simple cubic unit cell will be 4 by 3 pi r cube. It is the volume of one sphere and the number of particles per unit cell is 1, and hence the volume of particles per unit cell will be 1 multiplied by 4 by 3 pi r cube, that is 4 pi r cube divided by 3. Volume of unit cell, cubic unit cell, will be L cube and L is equal to 2r and it is equal to 2r whole cube, and it is nothing but 8r cube. It is the volume of unit cell and it is the volume of particles per unit cell, and accordingly The efficiency of packing can be calculated as follows. Efficiency of packing is equal to volume of particles per unit cell divided by volume of unit cell and multiplied by 100. The volume of particles per unit cell is equal to 4 pi r cube by 3, and it will be divided by the volume of unit cell, that is 8 r cube. On solving, we get 4 pi r cube divided by 3 and multiplied by 100 divided by 8 r cube. This will be r cube will be cancelled out, and it will be equal to 4 multiplied by pi into 100. The value of pi is 3.14 into 100 and divided by 8 into 3. 4 and 8 will be cancelled out by 2, and it is equal to 314. 314 divided by 6, and it is nothing but 52.3%. This is the efficiency of packing in simple cubic unit cell. It is 52.3%, and the packing fraction will be 0.523. That is, efficiency of packing divided by 100 is equal to packing fraction. Let us now consider body-centered cubic, that is BCC unit cell. Let the radius of particle or a sphere in BCC unit cell be r. This is the body-centered cubic unit cell in which this particle is present at the body center. This is the edge length of BCC unit cell. This is face diagonal, and it is nothing but root 2L, and it is body diagonal of the BCC unit cell, and body diagonal will be equal to under root 3L. In actual practice, these three particles which are present at the body diagonal touch each other. This particle is present at the body diagonal, and these two particles are present at the corners or vertices of the cube. This body diagonal, that is root 3L, is actually equal to 4 times of the radius. 1 radius here, 2 radius, 3 radius, and 4 radius. Root 3L is equal to 4r. And hence L will be equal to 4r divided by under root 3. The volume of particles per unit cell will be, it is the volume of one sphere 4 by 3 pi r cube, and the number of particles per unit cell in BCC unit cell is 2 multiplied by 4 by 3 pi r cube, and it will be equal to 8 pi r cube divided by 3. This is the volume of particles per unit cell. And now volume of unit cell, cubic unit cell, is equal to L cube, and L is equal to 4r by under root 3. And on solving, we get 64r cube divided by 3 root 3. This is the volume of BCC unit cell. And now efficiency of packing will be equal to volume of particles per unit cell, 8 pi r cube divided by 3, and volume of unit cell 64 r cube divided by 3 root 3 multiplied by 100. On solving it, we get 8 pi r cube divided by 3 and multiplied by 3 root 3 divided by 64 r cube and multiplied by 100. 3 will be cancelled out. 8 and 64 will be cancelled out by 8. RQ will be cancelled out, and it will be equal to pi into 100, that is 314. multiplied by under root 3, that is 1.732, and divided by 8, it is equal to 68%. The efficiency of packing in BCC unit cell is equal to 68%, and the packing fraction will be simply 0.68. Face-centered cubic unit cell, FCC unit cell. Here also the radius of the sphere is r. This is face-centered cubic unit cell in which particles are present at the vertices of cube and at the centers of all the 6 faces. This is the face diagonal of FCC unit cell, and it is equal to under root 12. This is edge length, this is edge length, and it is face diagonal, and it is equal to under root 12. In this diagram, the face diagonal is represented here. Under root 12 is equal to 4r. There are 4 radii in this face diagonal: 1 radius, 2 radius, 3 radius, and 4 radius. Under root 12 is equal to 4r, and hence L will be equal to 4r by under root 2. The volume of particles per unit cell will be 4 multiplied by 4 by 3 pi r cube, because there are 4 particles in FCC unit cell, and it is equal to 16 pi r cube divided by 3, and the volume of unit cell will be equal to L cube, and L is equal to 4r by under root 2, and on solving we get 64 r cube divided by 2 under root 2, and on simplifying we get 16 under root 2 r cube. This is the volume of FCC unit cell, and efficiency of packing will be calculated by dividing the volume of particles per unit cell, 16 pi r cube divided by 3, and divided by volume of unit cell, it is equal to 16 under root 2 r cube multiplied by 100, and on solving 16 pi r cube by 3, and it is again divided by 16 under root 2 r cube and multiplied by 100. r cube will be cancelled out. 16 will also be cancelled out, and on multiplying both numerator and denominator by under root 2, we get under root 2 into under root 2, it is equal to 2 multiplied by 3 is equal to 6, and in the numerator under root 2 is equal to 1.414, and multiplied by pi into 100, that is 314. On solving it, we get the efficiency of packing in FCC unit cell is equal to 74%, and accordingly the packing fraction will be 0.74. It is the efficiency of packing in FCC unit cell. And now let us consider hexagonal closed packed HCP unit cell. This is the diagram for hexagonal closed packed unit cell in which particles are present at the vertices, at the center of hexagonal faces, and in the body center there are 3 particles. This is the representation of the base of the HCP unit cell. In actual practice, the particle present at the face center touches all the 6 particles present at the vertices, and these particles also touch each other. This is the height of HCP unit cell, and it is the edge length of hexagonal face. There are 6 equilateral triangles here, and the edge length of triangle and the hexagonal face is equal to A, which is equal to 2r. A is equal to 2R. Area of the base. There are 6 equilateral triangles, and hence the area of this base will be equal to 6 multiplied by area of one equilateral triangle, and it is equal to under root 3 by 4a square. And a is equal to 2r, and hence on putting the value of a, we get 6 into under root 3 divided by 4 and multiplied by 2r whole square, and it is nothing but 6 under root 3 r square. It is the area of base of HCP unit cell. Here it is 4 will be cancelled out, and it is simply 6 under root 3 r square. The height of HCP unit cell is equal to 4r multiplied by under root 2 by 3. This height is equal to 4r multiplied by under root 2 by 3. It will be derived later on the next slide. Volume of HCP unit cell will be equal to area of the base. This base, which is equal to 6 under root 3 r cube, and multiplied by height 6 under root 3 r square and multiplied by height, it is equal to 4r under root 2 by 3, and on solving it we get 6 multiplied by 4, 24. Under root 3 will be cancelled out. Under root 2 r cube, r square into r is equal to r cube. The volume of HCP unit cell is nothing but 24 under root 2 r cube. Let us calculate the height of HCP unit cell. This is the HCP unit cell. As discussed earlier, it is the height of HCP unit cell, and it will be equal to h by 2. These 3 particles present at the body center of HCP unit cell touch each other, and on joining the centers of these 3 spheres, we get an equilateral triangle ABC, and O is the center of this equilateral triangle, which is joined to B, and a perpendicular from O is drawn on side BC, and it is nothing but OD. ABC is an equilateral triangle. In right triangle ODB, this is the right triangle ODB, this angle is equal to 30 degree. Cos 30 degree is equal to BD divided by OB. BD divided by OB, it is equal to cos 30 degree, and cos 30 degree is equal to under root 3 by 2. And BD is equal to radius of the sphere, it is R, and OB, and accordingly OB will be equal to 2R divided by under root 3. This is OB, distance between the center of sphere and the center in the vacant space. This is OB, this OB, and this particle is present above these 3 particles. This particle is present above these 3 particles as represented here. This is BE, which will be equal to 2R, and EO EO, the distance between this sphere and center of the vacant space, will be equal to h by 2. EO is equal to h by 2, and it is a right triangle. In right triangle EOB, BE square will be equal to OB square plus OE square. BE is equal to, as we have discussed earlier, it is equal to 2R. OB is equal to 2R divided by root 3 and its whole square plus OE square. OE square will be equal to 4R square minus 4R square divided by 3, and on solving it we get 8R square by 3 OE square, and OE will be equal to under root 2R. OE will be equal to under root 8R square by 3, and on solving it we get 2R multiplied by under root 2 by 3. It will be equal to 4R square into 2 by 3. The square root of 4R square will be 2R under root 2 by 3, and it is equal to h by 2, as we have discussed earlier. EO is equal to h by 2, and accordingly the height of HCP unit cell will be twice of this quantity, 4R under root 3. This is the height of HCP unit cell as used in the previous slide. Volume of HCP unit cell is equal to 24 under root 2 R cube, as discussed, as derived in the previous slide. The volume of particles per unit cell will be equal to 4 R cube into 6. Because there are 6 particles in the HCP unit cell, it is equal to 24 by 3 pi R cube. Efficiency of packing in HCP unit cell will be volume of particles per unit cell divided by volume of the unit cell. Volume of particles per unit cell is equal to 24 pi R cube by 3, and the volume of HCP unit cell is 24 under root 2 R cube into 100. R cube will be cancelled out. It is 24 multiplied by 3.14, that is the value of pi, into 100 and divided by 24 under root 2, and this 3 will come here. 24 will be cancelled out, and on solving it we get 74%, and the packing fraction will be 0.74. Thus, we have calculated the efficiency of packing in various types of unit cells, and let us summarize the findings of these calculations. The percentage void in HCP unit cell is 100 minus 74, and it is equal to 26%. In HCP unit cell, 74% space of the unit cell are occupied by particles, while 26% of the space is vacant. Now the time for self-assessment. Calculate the volume of vacant space in 20 centimeter cube of HCP crystal lattice. Here is the solution. Vacant space in HCP crystal lattice is equal to volume of crystal lattice multiplied by 26 and divided by 100, because the percentage void in HCP unit cell is 26%. 26 centimeter cube into 26 by 100, and it is equal to 5.2 centimeter cube. The volume of the vacant space in 20 centimeter cube of a HCP crystal lattice is equal to 5.2 centimeter cube. And the summary, the outcomes of these discussions are given here. This is unit cell, number of particles per unit cell, relationship between L or A and radius, efficiency of packing, and volume of the unit cell. In simple cubic unit cell, there is one particle, L is equal to 2R, efficiency of packing is 52.3, and the volume of unit cell is equal to 8R cube. In BCC unit cell, there are two particles, under root 3L, that is body diagonal, is equal to 4R. The efficiency of packing is 68%, and the volume of BCC unit cell is equal to 64R cube divided by 3 under root 3. In FCC unit cell, there are four particles. The face diagonal, that is under root 2L, is equal to 4R. The efficiency of packing is 74%, and the volume of unit cell is 16 under root 2R cube. And finally, in HCP unit cell, there are six particles. The edge length of the hexagonal face is equal to 2R. The efficiency of packing is 74%, and the volume of unit cell is 24 under root 2R cube. Thank you for watching the video with patience. Please like it if you find useful this video, and share it to your friends for their benefit. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.